Excellent. Thanks so much. All right, well, welcome everyone. Again, this is day 4 of the FreeFlyer Users Conference, and I'm super excited to be presenting again today. You may have seen my face already during the optimization talk earlier this week, but if you weren't around for that day, I'll just introduce myself again. My name is Julie Peck. I'm a member of the FreeFlyer technical support team and have been for about 3 years now. I was an intern with the company before I started full-time with the tech support team, so been having a great run with AI solutions so far. This topic is of special importance to me. My background is in physics and astronomy, so interplanetary analysis is like by far my favorite thing that I ever do in FreeFlyer. So I'm really excited about the conference today. I'm really excited to be here talking to you all. And without further ado, let's just jump right in. So we're going to talk about kind of a general overview of FreeFlyer's interplanetary capabilities today. That covers a wide range of things. I've tried to condense them into 4 bullet points here. So first we'll talk about celestial objects, ones that are built into FreeFlyer or custom ones that you can create on your own. We'll talk about different reference frames that are supported by FreeFlyer. And then we'll talk about 2 really cool objects, the rotating libration point and rotating pulsating system objects. There's a note on this page, just Michael already said, but remember that you're going to be muted during this presentation. If you do have a question, please post it in the chat box and Michael will ask me all of your questions at the end. So the first thing we're going to talk about today is the celestial object. So there are a number of built-in celestial objects in FreeFlyer. You can model planets, dwarf planets, asteroid comets, whatever you'd like. The built-in celestial objects by default are the 8 planets and the moon and the sun and Pluto, of course. We can't forget about Pluto. FreeFlyer also includes object presets for a variety of commonly used objects, different moons and things. And we'll be talking later about custom celestial objects, which you can use to model anything that is not on this list. So how do we model the motion of celestial objects in FreeFlyer? Positions and velocities of the built-in celestial objects are determined from the DE files or development ephemeris files that are generated by NASA JPL. So you can choose which DE file you want to use by changing your user preferences or through the FF solar system object, which we'll talk about in a little bit. FreeFlyer comes with truncated versions of the DE 200, 405, 418, 421, and 430 files. And it uses the truncated 430 file by default. I believe that goes out to about 2140. So if you do have a mission that extends past that time, you can load in a full version of the DE file, which is available from JPL. You can load those into FreeFlyer if you need to do analysis that is way further in the future. Orientation models. The Earth uses the IAU 1976-1980 nutation and precession model. The moon pulls the lunar nutation and libration from the DE file directly, and the orientation of all other planets or bodies is computed using the standard IAU-IAG attitude model. So I mentioned the FF solar system object when I was talking about the DE files there. A global instance of this object exists in every mission plan. It can be used to modify your default ephemeris files, station geodetics file, ionosphere modeling options. A lot of different just kind of configuration parameters are available through the FF solar system object. I wanted to call attention to a few right here on this slide that I think often get overlooked, and we get questions about these a lot. So these are 4 properties. They're compute polar motion, the CO update interval, NP update interval, and the apply UT1 correction properties. The first one just determines whether polar motion effects are going to be included in Earth's attitude modeling. That's set to true by default. The CO update interval, or celestial object update interval, is the update accuracy that's applied when reading state information from the DE file. So by default, this is set to 0, which is the instantaneous mode. And that means that we're just going to be modeling the position and velocity of all the celestial objects to the fullest accuracy possible. It's recommended to use this mode, But if you are running a low fidelity analysis, you can actually increase that value so that it is updated less frequently and maybe save yourself some computation time. The NP update interval is a similar property, and that is the accuracy that's applied when reading Earth's nutation and precession information from a DE file. By default, this is not instantaneous. Again, this is done just to save some computation time. It's set to 1800 seconds, which means that that is the rate. Every 1800 seconds is when those values get updated. I do want to make a note about this one in particular. If you're modeling a spacecraft in a LEO orbit or any orbit where Earth's orientation is going to have strong effects on your force model, you should set this to 0. Otherwise, you might see small divergences from other tools or from what you would expect when you're doing this modeling, because your Earth's orientation isn't being modeled to the fullest accuracy possible. The final one listed here is just a flag determining whether you want to apply the UT1 UTC time correction provided from the timing corrections file, which is ut1utc.dat, when you're computing the UTC time. And this one is set to true by default. Gravity models, how exciting. So by default, Earth uses the EGM96 potential model for modeling Earth's geopotential field. You can sub in a lot of different gravity models. FreeFlyer comes with 5 other gravity models specifically for the Earth's geopotential, and also includes a few different models available for the Moon and Venus and Mars. These are just common ones. You can also load in a custom gravity model if you'd like. And there's an example in the help file that shows how you would format that file to be able to read it into FreeFlyer. Other celestial objects are going to be modeled as point masses by default, anything besides the Earth. But again, you can load in any of these geopotential files that come with FreeFlyer or a custom one, and you can specify those for any body if higher fidelity is needed. So that kind of covers the built-in celestial objects, what's already packed into FreeFlyer. There's a good chance you might want to create a custom celestial object. So this can be used to model any bodies that aren't already available in FreeFlyer. Or, if you really want to replace our version of the Earth with your own, I'm not going to stop you, go for it. You can specify a central body for the celestial object, a gravitational parameter, equatorial radius, and flattening coefficient. All of that is used to compute the celestial object's motion and gravitational force. And they can be created through the object browser or through FreeFlyer script. So on the slide on the left here is an example of creating a celestial object through the object browser. In this case, the central body is Earth. All of these values are the defaults, so they probably look just like Earth, but you can change those to whatever you need. On the right, I've shown an example of creating a celestial object in script. I've very creatively called it my planet, and I set the central body and the radius. So in terms of modeling the motion of custom celestial objects, you can propagate using a 2-body propagator or a spice ephemeris. And these options are also available for the built-in celestial objects. So we talked about how by default we're going to use the DE files, but if you're trying to create a lower fidelity system for maybe a school project, or you just want to do a really simple analysis to start out your mission planning, you can reduce any celestial objects propagator to just a simple 2-body. And here I've just showed a couple of examples creating the celestial object to represent Io, one of Jupiter's moons. If we set it up with a 2-body propagator, we set the central body, change the propagator type to 2-body, and then you can use this handy set Keplerian state method to configure the Keplerian state of Io at the given epoch. If you use a spice ephemeris, it's a slightly different syntax, but you can read that in and use it as your propagator. And you just specify the file name, the observer, and the target, and change the propagator type to spice ephemeris. In terms of orientation, the IAU-IAG analytical model is available for a lot of different bodies. So if you're modeling some celestial object that's already included in this model, you can just simply select that. But you can also just pull in a custom analytical model and then specify the orientation using the alpha naught, delta naught, omega naught, and omega rate properties on the IAU-IAG Attitude Advancer object. This is just accessed through the CelestialObject.attitude model property, or again, you can create it through the object browser. You can also choose to not worry about orientation and just select no orientation updates. So by default, any user-created celestial objects are going to be modeled as point masses based on the gravitational parameter mu. If desired, we've already talked about this a little bit, but you can provide a custom geopotential file for higher fidelity gravity modeling. And the last note on this slide is just visualization. All objects except for the Earth are going to just be blank spheres in a FreeFlyer view window by default. I think also the moon includes a texture by default. But you can load in image files to apply textures to any object. Like on this slide, we've applied a texture to Jupiter and also to Io. So now that we've kind of covered what celestial objects are and what they mean in the context of FreeFlyer, how do we actually interact with them from a spacecraft? Because of course, the spacecraft object is the heart of FreeFlyer. So the first thing we would need to do is set the central body. All your spacecraft properties like position, velocity, and the Keplerian orbital elements are going to be reported with respect to the spacecraft's central body. An easy way to get a spacecraft's MJ2000 position or velocity with respect to any celestial object is just to change the central body. This does not change the spacecraft's state. So if you are orbiting the Earth, but you want to know what your position would be with respect to the moon, you can just change the central body to the moon. Your spacecraft's orbit, state, force model, none of that changes. You can report out the position and then just change it right on back to Earth. And then you would go back to retrieving the position with respect to the Earth in the MJ2000 frame. This is a really important note. Don't forget to add all bodies in your analysis to your spacecraft's force model. I have done this before. It's embarrassing every single time. If you want a spacecraft that's orbiting Mars and you set it all up properly, you do actually have to turn on Mars's gravity in the force model, or else your spacecraft will fly right past Mars and you'll be like, why did this happen? What have I done? So this is a really important note, and it's always funny when I realize that I've forgotten to do that. But don't forget to do that. You can set this up through FreeFlyer script, just like anything else, using the add force method on the force model object. Or you can just configure it in the object browser if you've built any of your custom celestial objects through the object browser as well. So over here on the right is a picture of the force model page of the spacecraft object editor. And it includes all of the built-in bodies, the 8 planets, Pluto, Moon, and Sun, as well as a custom celestial object that I created in the object browser called My Planet. And through the object browser, all I have to do to turn it on or to turn its gravity on is give it a check mark in that checkbox. So I'd like to take a look at one of our sample mission plans. This one is the Rings of Jupiter. So this is FreeFlyer. Hopefully you've seen it before by now, but if you haven't, welcome. We're happy to have you. This is the home page, and you can access all of FreeFlyer sample mission plans by clicking the Browse Sample Mission Plans button. This pops up a Windows Explorer window that just goes right to your sample mission plans directory. I'm going to go into the Interplanetary Analysis folder and select Rings of Jupiter. So here's an example where we're using a lot of the topics that we were just talking about. Over in our celestial objects section of the object browser, we have 4 custom celestial objects to represent all of Jupiter's Galilean moons. So I can just click on one to open that up. You can see the configuration here. We've set the central body to be Jupiter. We've set a gravitational parameter, radius, and flattening coefficient for Callisto. We're using a SPICE file for propagation. And we are using the IAU-IAG analytical model for orientation updates to Callisto. Similarly, we were just talking about force models. Make sure that your spacecraft's force model includes all of the celestial objects that you want to include in your analysis. So here we've turned off the Earth, actually, because we don't need it for this analysis. And we've turned on Jupiter and the 4 moons so that we're getting that gravity incorporated in the force model. I'll go ahead and run this. So this is a really important note, right? You can do the same things with custom celestial objects as you would do with any of the built-in celestial objects. So in this case, we're doing contact analysis, and we're performing maneuvers on a spacecraft that is orbiting Jupiter. It's getting closer and closer to Jupiter with each maneuver, performing a series of Hohmann transfers. And all the while, it's performing contact analysis with the 4 Galilean moons. Make this a little bit bigger. We're drawing contact vectors here between our spacecraft and the moons to show when contact is achievable. Hopefully it's not lagging too much on the screen. You'll also notice Jupiter is just a plain sad ball right now. So if I wanted to, I can open up my properties editor and turn on a texture for Jupiter. So any of the built-in celestial objects, you can just select Use Image, and we have a built-in texture file. For any of the other ones, you would need to browse to your own image file, but we do support loading in any image file to supply texture for any of the custom celestial objects. Also, as a note, just in case anyone's curious, we're representing the rings of Jupiter here with proximity zones based on the celestial object. So I just think that's a cool little visualization tip. So returning to the slides, I'd like to talk about the different reference frames that are incorporated with FreeFlyer, because these become especially important when you're doing interplanetary analysis. So FreeFlyer has built-in support for various reference frames. I'm not going to read every single one of them to you here, but here they are. They're all described in detail on the Orbit Reference Frames page of the help file. And this includes Earth-based frames as well as Moon-based frames. In addition to that long list of built-in reference frames, all celestial objects, built-in or custom, also have 3 generic built-in frames that come with them. So you can access a body fixed frame for any celestial object. That's a rotating frame just based on the attitude model for that body. You can access an inertial J2000 frame, which is the body frame evaluated at the J2000 epoch, and that's a non-rotating frame. Or you can access the inertial at epoch frame, which again is just the body frame, but evaluated at a user-specified epoch, and it is a non-rotating frame. The way you get to these in script is through the reference frame IDs property. So here I've just shown an example of accessing these 3 built-in frames for Mars by using that reference frame IDs property. The get and set Cartesian Keplerian state methods allow for really easy setting and retrieval of states in any of the built-in frames. So this is a really handy utility. You can use this to set your spacecraft state in just 1 line of code, which is awesome. In this example, the first line here is setting a spacecraft's Keplerian state by passing in an array called Kep elements, which contains the Keplerian elements, and it's using the Mars inertial J2000 frame to specify that Keplerian state. In the second line, we're retrieving the Cartesian state with regards to the moon fixed frame, and that just passes in an integer argument, which in this case is 9. And all the documentation for these methods show various different overloads that you can use and includes guidance on what arguments mean which reference frames and all of that. There's also a handful of conversion functions, which again, I think sometimes get overlooked and they're so useful. So everyone make sure if you've been dozing off to tune in for the conversion functions. Position convert, velocity convert, and position velocity convert are really, really handy utilities that allow you to just easily convert any spacecraft state from one frame to another. In this example, I'm just showing the syntax for converting a spacecraft state from MJ2000, which is, again, what you're going to get from the position and velocity properties, into the Moon PA frame. Now you might be saying, well, what if I want to convert to or from a frame that FreeFlyer doesn't support by default? Well, you can create a custom coordinate system. So the coordinate system object lets you define custom coordinate systems in a number of different ways through the build coordinate system method on that object. I've listed out all the different ways here. Of particular relevance is by using the body coordinate system of a spacecraft or celestial object. These are super handy. And then you can convert vectors to and from any custom coordinate systems using the convert to or from coordinate system method on the vector object. So all you would need to do if you wanted to get your spacecraft's position into a custom coordinate system is assign your spacecraft position to a vector object using the element property, and then use the convert to coordinate system method on that vector object to convert into your custom frame. I do want to make a note here about coordinate systems. We leave it up to the user to determine what the coordinate system is referenced from. So by default, if you create a coordinate system object and then retrieve its rotation matrix, it's going to be a rotation from MJ2000. But if you start chaining coordinate systems together, we do leave it up to the user to make sure that they know which coordinate system is referenced to or from, which one goes forward or backward. So just keep that in mind when you're using these conversion functions, because if you are trying to get back to MJ2000, you want to make sure that you don't have any rotations in between your current coordinate system and MJ2000. Moving on, kind of tangentially related, similar to reference frames, but a different topic, I want to talk about rotating libration points. So what is a libration point? If you've done a lot of interplanetary analysis, you're probably pretty familiar with this term. But if you're just starting to learn, a libration point or a Lagrange point are points near two bodies or systems where the gravitational forces cancel out so that that point is stationary relative to the system. So L1, L2, and L3 are collinear between the primary and secondary systems. And then L4 and L5 form equilateral triangles with the positions of the primary and secondary systems in the orbit plane of the secondary about the primary. That was a lot of words, but it looks like this diagram over here. You can define a coordinate system at each of these libration points that rotates with the system. And that's a really handy configuration for describing dynamics like the circular restricted three-body problem. So in that case, you would have a primary and a secondary gravitational body, where your spacecraft is the third. And this can be a really, really useful frame for establishing stable orbits with respect to these libration points. So to model this in FreeFlyer, you can use the aptly named rotating libration point object. This lets you set up your primary and secondary objects. They can be single celestial objects or celestial systems. And I've bolded celestial systems here because I do want to call out that you can set up multiple bodies and treat that the barycenter of that system as your secondary in the rotating libration point frame. So the script here demonstrates how you might do this to set up the L1 Lagrange point for the Sun, Earth, Moon system. In this case, the primary body is the Sun. The secondary is the Earth, Moon system. So we've added two bodies to create a celestial system. Or you can create the celestial system separately, just in case you want to use any of the utility methods on that object. And you can add that to your rotating libration point as a whole system as well. Finally, all you need to do is choose which libration point the object will represent. So once you've added the primary and the secondary, you have all the bodies configured, everything that you need, and then you just select which libration point you want to model out of the 5. So there are a number of handy interfaces on this object. that provides simple ways to do things like getting your position or velocity of the rotating libration point with respect to a reference frame or to the reference body. So in this case, the reference body is Earth, and we just want to get the position of L1 with respect to the Earth. You can use the get position at epoch method on the rotating libration point object. You can also get the orientation of the RLP frame with respect to MJ2000 using the get DCM at epoch method. And you can get and set positions and velocities of spacecrafts or other objects in the RLP frame as well. So if you want to retrieve the moon's position, you could use get position of object. And if you want to set up a spacecraft state, you can use the set spacecraft state method on that RLP object to specify your spacecraft, which frame you want, which origin you want, and the spacecraft state. It's also really easy to create visualizations in this frame. You saw an example at the very, very beginning of this slideshow in the GIF that was playing of a rotating libration point frame. It's an object that is already rotating with the system, so all you need to do is configure your view window to use a body fixed view and set that source and object or source and target to the rotating libration point object that you've configured. So I want to pull up another sample mission plan to take a look at here. This will be the libration point orbiter sample mission plan. Let me close the rings of Jupiter. And again, I'm just going to my Browse Sample Mission Plans button into the Interplanetary folder, and this time selecting the libration point orbiter. So in this case, we can see exactly what we were talking about in the slides. We're configuring the RLP frame by adding the sun as a primary body and the Earth and Moon as the secondary system. We set the reference body to Earth, so any position retrieval for the L1 object will be with respect to the Earth. The visual scale is just for visualization purposes. And we did this first this time. We specified that the libration point will be L1. Now, the really exciting part about this is that you can set up your spacecraft state in this frame instead of having to do it in MJ2000. So I just want everyone to take a look at how simple this is. Our spacecraft's orbit is being configured with respect to this rotating frame. So we're using really nice round numbers. It doesn't have to be anything crazy. The velocity with respect to L1 at the start of the orbit is just going to be 0. And then we just configure, we set the spacecraft state using that handy utility method on the L1 object. And then you can easily report out all of these different properties just by storing that spacecraft state in an array. This can even be used, as we're going to see when we run this in just a second, for complicated things like targeting. So in this case, we'll be targeting, we'll be calculating the Y velocity that's necessary to maintain a stable orbit around our libration point. And we're passing these values in and using these utility methods within the targeting loop to get that desired velocity. So I'll go ahead and run this. All of these views that we're seeing are body fixed views on the RLP frame, so you can see the axes of each frame. They're just looking from different directions so that we get a view of each different plane. And with each passing of the, with each y=0 plane crossing, the FreeFlyer target command is being used to determine the required Y velocity in order to maintain the orbit with 0x velocity at the next y=0 crossing. So in this case, we're not actually performing any maneuvers. We're just updating the spacecraft's Y velocity at each plane crossing so that we maintain that stable orbit. But this would be really easy to apply to a maneuver. Once you know the desired Y velocity, you can just subtract the current velocity from that, and you have the necessary maneuver to maintain your stable orbit. I also just think that these views look really nice. As we can see, the sun is our primary body. We've drawn a line between the primary and the secondary here. The The secondary in this case is the Earth-Moon system. So the barycenter is going to be close to the Earth because the Earth is so much more massive than the Moon, but not exactly at its central location. And the frame itself is rotating so that this orbit looks nice and clean around L1. So I've got one more topic that I want to go over, and that's the rotating pulsating system. So a rotating pulsating system, or RPS, as I might abbreviate it going forward because that's a lot to say, is a reference frame that's built around two bodies, similar to the rotating libration point. And in this case, the frame rotates with the two bodies about the barycenter, and all distances are scaled so that the distance between the primary and secondary remains constant. That's a bit of a mouthful, but you can imagine that it is rotating and the distances are being scaled and updated constantly so that the primary and secondary appear to be still. To set this up in FreeFlyer, you'll configure the reference distance and reference vector properties on the rotating pulsating system object. So the reference distance is going to be that distance that's used to calculate the scale factor for the frame. You generally want to choose this to be the approximate distance between your primary and secondary body. And then the reference vector is just the second vector that's used to define the frame, where the first is between the two bodies, and the third is the completes the right-hand rule for those two vectors. So you can choose three different options for your reference vector. First would be based on relative velocity. So this is the ideal choice when the secondary object is orbiting the primary, like the Earth-Moon system, for example. You could choose based on the MJ2000 Earth equator north direction. This can be useful for kind of specific Earth spacecraft geometries, like a geosynchronous orbit, or based on the MJ2000 Earth ecliptic north direction. So this would be useful for the case where the secondary object is not orbiting the primary. So maybe something like Earth-Mars. Mars, of course, is not orbiting the Earth. They're both orbiting the Sun, but you can still create a rotating pulsating system such that it rotates with the rotation of the Earth and Mars relative to each other, and then pulsates based on the distance between the two of them. To configure the primary and secondary objects, it looks pretty similar to the rotating libration point actually, but you can only use objects in this case, not a celestial system. So you set the primary object, you set the secondary object, using methods directly on that rotating pulsating system object. You set the reference distance and reference vector through those appropriate properties, and you choose whether to use the pulsating mode. This is turned on by default, but you can turn it off if you want to see the distance change between your two objects. Like the rotating libration point, the rotating pulsating system contains convenient methods for retrieving information both about the frame and for getting and setting object states within the frame. So these look very similar to our RLP. We can use the set spacecraft state method to set a spacecraft's position and velocity in that RPS. And you can get the position and velocity of any object, spacecraft or celestial object, just by using the get posval of object method. This is also a particularly useful view. So it can be really interesting to look at a system where in the view, the distance isn't changing while it's rotating with it. So this lets you generate 3D output in a rotating pulsating frame. It's a specific viewpoint type available through the view window object. Over on the right-hand side, we see how we could set this up through the object browser. So if you create a view window in the object browser, you can specify your primary, your secondary for this view. You can tell it whether or not you want to be pulsating. You choose your reference vector. All of the same stuff that you could configure in FreeFlyer script is actually available for the viewpoint specifically through the view window. So if you set this up through the view window, instead of creating the rotating pulsating object in script, you can actually initialize it from your view parameters in FreeFlyer script. So I've included an example here showing how you would do that. If you have a rotating pulsating system object called RPS, You can call initialize from rotating pulsating viewpoint and pass in the viewpoint that you want to use. And now your RPS is all set up with your primary, secondary, and all of the configuration options, and you don't actually even need to do anything. So that's pretty cool. I've got an important note here. This has come up a few times with customers that I've talked to. When you're using a rotating pulsating view with a relative velocity reference vector, the primary and secondary objects have to be configured so that the view window stores their velocities. This manifests as a checkbox in the view window object editor, which we'll take a look at in a minute. But you can also set this through FreeFlyer script using the set object store velocity method. So the reason that this is important is that in order for the view to know how to define this rotating pulsating system, how to define that second vector, it has to store the velocities of the primary and secondary objects because it's using the relative velocity for the reference vector. This is not stored by default, again, just because it's not normally needed for other view configurations. But for this specific one, you want to make sure to turn this on. Otherwise, you might not see your spacecraft tail, and then you'll be like, where is my spacecraft? What's going on? So we're going to take a look at a sample mission plan that uses this rotating pulsating view, and that is the Earth to Moon analysis. Close this. This is available in the Interplanetary folder, but it's also listed here in our demonstration mission plans section just because it's so cool. So if I click that, it will start running immediately because it's one of the demos. And you see this really interesting view at the top, which I'm actually going to go ahead and just make bigger. And then I'm going to zoom out so we can see both bodies. In this case, we're plotting a spacecraft's trajectory on a transfer from the Earth to the Moon in the rotating pulsating system. So the Earth and Moon are staying, they look constant with respect to each other because the pulsating mode is enabled. And we're getting this really interesting view of the trajectory. And it looks so simple and straightforward because of this really unique view that we're utilizing. So you can move this around. Currently it's set to use the center as the middle of the view. Just going to reconnect the standard here. I did want to, I'm going to run this again, but this time I'm going to turn off the pulsating mode for this view because that gives you kind of a different perspective. So I'm using the replay feature here. I'll open the properties editor. And these are the options for the rotating pulsating view. I'm going to uncheck enable pulsating mode. And close that. And now if we run this, the Earth and the Moon are not staying at the same distance with respect to each other. And we can see that each time the simulation gets reset to try a different trajectory, the Moon scooches in and then it scooches back out. And we can see the spacecraft's orbit is around the Moon, so it's moving along with it in that frame. And you can just easily switch between these two by turning that checkbox on or off. So if I turn it back on, now our orbits are back to what we were seeing originally. I want to take a look at how this is actually set up in FreeFlyer. So this is our view window, the rotating pulsating view. On the viewpoints tab, we have our primary and secondary objects, the Earth and the Moon. We set our reference distance to be approximately the distance between the two of them, and our reference vector to use the relative velocity because this is a situation where the secondary object is orbiting the primary. Turn pulsating mode on. And on the content page, if you're setting this up through the object browser like it's shown here, this is where you want to check that store velocity box. So I've just selected the Earth and store velocity is turned on. Same deal for the Moon. It is not turned on for other objects like Jupiter, which I just randomly selected. So if I turn these off, I want to show you guys what happens if you don't remember to configure those. you just see a spacecraft and no tail. So we can sort of see it zooming around there. If you can see that little blue dot, now it's red, but our tail isn't being drawn. And that's because we didn't store the velocities of the primary and secondary objects to our view window. So I'm going to fix that because it's bothering me. And we'll turn both of those back on. Back on, there we go. And now we're back to normal. We've got a couple of other views here as well. Just a lot of different things that you can do with FreeFlyer, a lot of different configurations you can set up. Here's what it might look like from the moon's perspective in a view that's fixed on the moon. And here's an Earth-centered view of the transfer to the moon. Just seeing all these different trajectories that we're trying. So that brings me to the end of this general overview of interplanetary topics in FreeFlyer. You might have thought to yourself during this, well, a lot of this is stuff that I've been doing before in FreeFlyer, and that's true. This is not new with FreeFlyer 7.6. However, a lot of these capabilities were added as convenience methods, especially in FreeFlyer 7.4. So if you're a student particularly, these are some really useful improvements. We've made it a lot easier to simplify your system. It used to be kind of a pain to set up an Earth that was just being modeled as a point mass or as being in a perfectly circular orbit around the sun. Now it's a lot easier to set up that kind of thing using the new two-body propagators that are available for celestial objects. So that's a really helpful option. And so that was added with 7.4, but a lot of this has been possible in FreeFlyer for a really long time. We just want to make sure that everyone's aware of these cool features as interplanetary missions are becoming so much more popular and interesting. If you're looking for additional resources on this stuff, there's an entire interplanetary analysis guide in the FreeFlyer help file. There's also a large selection of sample mission plans. We saw a few today. And I definitely encourage everyone to stick around for the rest of today's FreeFlyer Users Conference. I'm super excited to see these talks. I think they're going to be really, really cool. We have Dr. Diane Davis talking about gateways near rectilinear halo orbit, which is really, really awesome. We have Michael Volley talking about a lunar navigation constellation design, and then Brian McCarthy going over a two-level targeter for transforming from the circular restricted three-body problem. Of course, we've said this a lot of times throughout this week, but if you ever have any questions or suggestions or feedback, please reach out to our teams. I've got the contact information for the technical support and sales teams here. We're always happy to hear from you, and we love getting user feedback, so don't hesitate to chime in. That's all I have for today. So I am happy to take any questions, and I believe Michael will be reading those up.
All right. Thanks, Julie. Thanks for taking the time to tell us about all the different ways that you can use FreeFlyer for interplanetary analysis, visualization, all those cool views. Just a couple questions from our audience about the celestial object. Could you use it for an asteroid?
Yeah, you could absolutely use it for an asteroid. You can even load in custom gravity models if you needed to model specific gravity for that asteroid. You know, gravity for an asteroid can be a little bit finicky, so you can pull that in and use the custom geopotential models there. I also have a fun trick. You can use a 3D model and set a spacecraft at the center of your asteroid if you want to show that asteroid as something other than just a ball. So that's a really neat visualization tip.
Awesome. What deep space missions have used FreeFlyer in the past?
Oh man, well, a lot, I believe. I know JWST is using FreeFlyer for mission planning, so hopefully when that launches someday, that'll be running with FreeFlyer. We're using it for launch window analysis right now. We're also doing planning for NASA's Gateway, which Diane will be talking about right after this talk. And that's being used for contact analysis, for trajectory design. I know they were analyzing where the window was looking on the spacecraft using FreeFlyer, because this is a human mission, of course, and we want to make sure that our astronauts are happy. So there are definitely a lot of applications that FreeFlyer is being used for. I think there are probably more that Michael might be able to speak to.
Our team is telling me that we've also got the missions over at L1. So ACE, WIN, SOHO, Discover, all of those NASA missions used FreeFlyer or are using FreeFlyer.
Very cool.
Why do you have the majority of celestial objects turned off by default for a spacecraft?
Sure. Well, it doesn't really, you don't need them on, generally, is the answer. You can turn them on if you're getting into really, really high fidelity final stages of your analysis, but the more and more complex that you make your force model, the more computational power it's going to take to run your simulation. So if you don't need to model the gravity of Pluto because your spacecraft is in orbit around the Earth, it's probably not necessary. You can just call that negligible. But you can turn all of these on and run as many bodies in your force model as you want, depending on how high fidelity you need your analysis to be.
Gotcha. I think the last question that I have so far is, could you export a celestial object that you have set up?
Yeah, so you can export your custom celestial objects as FreeFlyer object files if you want to share them among multiple mission plans. You can also generate SPICE ephemerides using your celestial objects or your spacecraft through FreeFlyer. So there are a lot of different ways that you can export those and share them among mission plans.
Great. A couple more have come in here. What about SRP modeling for deep space mission?
What about SRP modeling? Yes, you can turn on SRP modeling in FreeFlyer. That's also through the force model object. I'm just going to pull that up over here real fast. I'll just create a new mission plan because I accidentally closed that one. But if you go to the force model page of your spacecraft object, you can check this little solar radiation pressure box, and that will model SRP during propagation. And that works for whether you're in Earth orbit or in interplanetary orbit around any celestial body.
Gotcha. Our team here is letting me know, just a reminder back to Monday's presentation with product manager Sarah Fields, that the SRP that we have now is a cannonball object. However, we are in the next version of FreeFlyer in 2021 looking at upgrading that to other more higher fidelity SRP modeling. So if you're interested in that for interplanetary missions and for other uses, please drop us a line in the chat or let us know.
Yeah, for sure. I'm really excited to see that come in as a new feature. That's going to be really useful.
Yeah, another question has come in. Can you do orbit determination for an interplanetary mission with FreeFlyer?
Absolutely. You absolutely can, and I would recommend that everyone stick around for Michael Volley's talk coming up later today. This one, Lunar Navigation Constellation Design, where he'll be touching on that.
Great. Questions keep coming in. What about patch conics modeling, like I learned about in school?
Yes, you can do patch conics modeling in FreeFlyer. We actually have our FreeFlyer University guide, which is available on our website, includes a step-by-step walkthrough of setting up a patch conics problem. So I definitely recommend taking a look at that. We also have a couple of new examples specifically related to our optimization features as well, which are new with FreeFlyer 7.6, that include that type of design. So everyone take a look at some of the new sample mission plans, and that university guide page would be especially helpful if you're trying to learn more about the patch conics approach and how to use it in FreeFlyer.